Coming up on Factory Made, how 416,000 shiny gold dollars start with a lump of clay. Then, a spin cycle that pulls more G's than a fighter jet. And how to build a fishing rod 3 times stronger than steel. The United States Mint produces 15 billion coins a year. The Mint in Philadelphia has been making them since 1793. Each new coin begins with a freehand drawing. Months before a coin is slated for release, one of the Mint's staff artists begins work on a design. This one for a new limited edition dollar coin in a series featuring all of the past U.S. presidents. In this case, it's John Quincy Adams. Using contemporary portraits as a reference, he creates a sketch. Once the sketch meets the approval of the Treasury Secretary, the artist begins the process of turning a pencil drawing into genuine coin of the realm. The image is scanned in high resolution. Then the artist sets the portrait against a template of the finished coin. He smears clay onto a palette 12 times the size of the finished coin. Then uses carbon paper to transfer the image. Why clay? Because the image on a coin is actually a very shallow sculpture.
I think the most challenging part of the sculpture is getting a likeness and having it be alive, having the eyes look like they're really looking out at you and not just a dead-looking flat portrait. It has to have relief. It has to look like it's three-dimensional, even though the relief is so small.
That's a tall order when you're working in shallow clay. The key to the 3D effect is in the fine details. Those little touches don't just bring the portrait to life. They also ensure that the coin is almost impossible to forge. The next step is to make a plaster mold from the clay model by putting the clay in a plaster bath. Once the plaster mold dries, it's used to make a plaster cast, which looks a lot like the original clay sculpture, but it's much sturdier. Now, the cast goes back to the artist for fine-tuning. When you're going to be in circulation for many years, you want to look your best. John Quincy looks pretty good in plaster. But how do you get all that detail onto a coin that's only a little thicker than a credit card? The Mint uses a technique called photogrammetry to create a 3D image. With paper reference points affixed to the cast, a photographer takes 48 pictures from 6 angles. Next, a sophisticated camera scans every detail of the mold. Then, once the images are fed into the computer, a flat picture becomes a topographic model of the 6th president's face. A technician checks to be sure that the relief peaks and valleys aren't too high or deep for the coin. If John Quincy's nose extended too far, it would get cut off. And that would definitely spite his face. Anything too low could put a hole in the coin, not to mention damaging the multi-million-dollar machine used in the next stage of the process. The Computer Numerical Control, or CNC, reads the computer rendering and sculpts a disc of tool steel into what's called a master hub. It takes the Mint 30 hours to carve the president's face into a metal disc. It's a painstaking process that demands the utmost precision. Tiny carbide mills remove layer upon layer of metal with a cutting edge that's just twice the thickness of a human hair, and gradually turns this lump of solid steel into an exact rendering of the original sculpture, only smaller. The mint now has a scale-sized replica of the coin. But to make copies, they need a reverse image, called a die. Next stop, the hubbing machine, which puts John Quincy under more pressure than he ever experienced in the White House. In one big squeeze, 180 tons of pressure transfers the president's likeness onto the die. Under this much force, a metal chip could easily splinter off, with potentially fatal consequences. So all hubbing is done behind the safety of bulletproof glass. The mint will produce a master hub for each presidential coin. The dies are inspected under a stereoscope. Every detail is scrutinized. Inspectors give no quarter when it comes to legal tender. A single imperfection could ruin a whole run of 250,000 coins. At the United States Mint in Philadelphia, President John Quincy Adams is about to get his face stamped on a new $1 coin. The coins are made of manganese brass, delivered to the mint in 4,400-pound rolls. It's not gold, but it kinda looks like it. And it has the same electromagnetic signature as earlier dollar coins, so it'll work in the soda machine. After the roll is hoisted onto a spool, it begins to unfurl, and a worker feeds the end into a machine called the blanking press. This giant hole punch presses out 3,300 blanks per minute. It may look like a Vegas jackpot, but until they're minted, these blanks are just chump change. The blanks next roll through an upsetting mill, which gives the center of each blank a big squeeze, popping out the edges to form a rim. These raised edges are a critical part of the coin's anatomy, because the rim is the highest point on the coin. It'll protect the faces from wear and tear. At room temperature, the blanks are too hard to take a good imprint, so they're heated to 700 degrees Fahrenheit to change the metal's molecular structure. All this heating and cooling leaves the blanks a little dingy, so it's into a washing machine that spins the blanks with BBs and a chemical solution to give them a spit shine. After an hour in the bath, 2 tons of blanks are finally ready for minting. Inside the minting machine, dies stamp on the heads and tails. Otherwise, the dollar pieces wouldn't be much good for coin tosses. They also imprint a feature unique to this line of coins. The traditional "In God We Trust" is pressed right into the rims. These John Quincy's pass muster, and this run of brand new dollar coins is complete. In just 8 hours, one roll of manganese brass has been transformed into U.S. currency worth $416,000. And John Quincy Adams finally gets his little piece of posterity. What finely engineered piece of equipment is made of surgical-grade stainless steel, generates more than 60 times the G-force of a space shuttle launch, and also tackles ring around the collar? Time to pay some respect to the workhorse of the laundromat, the Dexter commercial washer. This modern marvel has over 650 parts, and after it cleans your clothes, it takes them through a dizzying 700 RPM spin cycle that packs an incredible centrifugal force of 200 Gs. G-force is a measure of acceleration. Each G equals the force of gravity on Earth at sea level. Astronauts endure 3 Gs at liftoff, 5 Gs and you pass out. But 200 Gs will wring the last drops of water from your jeans and towels in just 4 minutes. This machine is designed not only to withstand that kind of force, but to run 16 to 20 hours a day for 20 years straight. That's about 36,000 wash cycles before it retires. And even that's not enough to counteract the power generated by this washer. When it's finished, it'll need to be bolted to a concrete floor, or the entire 1,100-pound machine could buck and skid its way across the laundromat floor. The apparatus that helps get the drum spinning with such force is called the spider. The shaft starts out as a bar of steel, which is cut to size and then sculpted by a grinder into a tapered shape. The fit between shaft and bearing house needs to be exact. There's only wiggle room of 1/10,000th of an inch. The spider's shaft gets welded to its legs, and the whole structure will be attached to the inner drum. The inner drum spins the clothes. The outer drum holds the water. Designed for life in a wet and soapy environment, both layers are made from rust-resistant surgical-grade stainless steel, which arrives in pallets at the factory. The sheets that become the inner drums get as many holes as can fit on them without actually destroying them. The holes, all 4,736 of them, have to be big enough to let the water flow, but small enough not to swallow buttons or catch on the clothing. The operator has to move each piece through the press manually. Fail to line up the sheet correctly, and it'll be scrap in the blink of an eye. Workers curl each sheet into a roll and weld the ends together. Finally, the drum's tops and bottoms get welded on. Everything has to be even and tightly welded, or else the drum will never spin smoothly. The finished drums have to be strong enough to hold up under those intense G-forces. How strong? They make them out of the same stuff they use to build bridges and skyscrapers: structural steel. Anything less couldn't handle the drum's spin cycle. When you're making washing machines designed to survive 200 Gs dozens of times a day in these close quarters, you don't want to leave anything to chance. So the folks at the Dexter Washing Machine Company would rather make the most critical components themselves than rely on anyone else. This is the bearing housing. Its job is to absorb the energy from the machine's whirling drums, and it has to be cast perfectly, or the washing machine might become dangerously unstable. To make a bearing housing, scrap iron, steel, and a kind of furnace fuel called coke are fed into a giant melting pot called a cupola. The coke helps raise the temperature to the melting point, about 2,800 degrees. This holding furnace keeps 40 tons of molten metal hot until it's ready to be poured into silica sand molds. It takes between 30 and 90 minutes for the metal to set. Now, to make a whole greater than the sum of its parts. The inner drum goes on top, and 4 long rods are bolted in. Then the worker trues up the assembly. This gauge makes sure that the center line of the drum lines up with the center line of the shaft. If it's off by even a fraction of an inch, the machine will have a very short and very violent career. Of course, the washer needs a motor and some plumbing. And now the most burning question of all. Why is a washing machine door made out of glass? Believe it or not, it's because customers love to watch their clothes swish around in the suds. With all the circuitry installed, workers install the part dear to the heart of every laundromat owner, the money slot. These washers can be fitted with a traditional coin slot or a modern debit card system. An inspector runs each finished machine through a full 23-minute cycle to check for leaks. Once a washer passes muster, workers slap on some stainless steel outer panels. And after just a day on the production line, this gleaming Goliath is ready for a lifetime of dirty work. Humans have been using fishing rods ever since the ancient Egyptians first dipped a line in the Nile. Rods are a good idea. They allow anglers to keep their distance from the fish and not scare them away. But they have to be strong too, so you can reel in the big one. Now, carbon fiber has made it possible to build the perfect rod. Not only long enough, but light, flexible, and tough. It begins with carbon polymers spun into a fiber with 3 times the tensile strength of steel. The manufacturer lines up the fibers in a single direction and creates a fabric by infusing them with a sticky resin.
So it's in a sheet form like this. And at that point, it also gets the resin impregnated. I can rip it real easy this way, but I cannot this way.
A very thin woven fiberglass lining reinforces the sheets. When the resin is activated, carbon fiber becomes extremely malleable. And because it's so light and strong, you can find it in everything, from race cars to airplanes and satellites. And of course, fishing rods. Fishing rods need to be strong, but they also need to be sensitive. Carbon fiber rods are light enough to pick up the slightest tug from a curious fish. At St. Croix Rod in Park Falls, Wisconsin, a worker begins the process of making a fishing rod by cutting the carbon fiber sheets into triangle-shaped patterns that will form its core. Before the patterns are rolled up, a worker irons a second layer of carbon fibers onto the strip at right angles to the main fibers. This helps prevent the tube from collapsing if you happen to snag your hook on a really big fish. This is a sample tube that hasn't been treated with the second fiber sheet. It breaks easily under pressure. This treated sample bends, but doesn't snap. To give the rod the right shape and diameter, it's wrapped around a metal rod called a mandrel. A 200-degree iron activates the sticky resin that binds the carbon fiber and glues the edge of it to the mandrel. Now, the patterns are ready to roll. A worker places them in this rolling machine, which tightens the fiber strips around the mandrels and creates a snug tube. Heat-resistant tape holds everything tightly together, while a huge 260-degree oven activates the resin in the fiber. When the rod blanks come out of the oven, they're hard and their shape is set. But what would a fishing rod be without its handle? Cork might seem like a very low-tech material to stick on the end of a space-age rod, but builders use it today for the same reason it's been used for thousands of years. Not only is cork light, buoyant, and durable, but it makes for a warm, comfortable handle in cold conditions because it doesn't absorb water. Occasionally, rods are pulled off the production line for strength and flexibility testing. This machine goes by the name Dynamic Analyzer. Actually, it could just as easily be called JAWS. It pulls and twists the rods to simulate a big fish fighting the line. It can exert 1,800 foot-pounds of torque, 3 times as much as a pickup truck. JAWS tests the rods to their limits and beyond. You can learn a lot from the way a rod snaps. If it breaks in just one place, it's a lemon. But if it breaks in several places, it's a well-made rod. You've just asked more than it was designed to give. After 30 days of manufacturing and 5 inspections along the production line, the final approval comes down to an inspector's persnickety eye. This carbon fiber rod is ready to go fishing. And after all that work, it weighs less than 4 ounces. A lot less than that tasty trout fillet you're hoping to bring home for dinner.
接下来，超级强权大比拼，北美重型机器挑战欧洲钢铁怪兽，超猛机器王，欧美大赛就在 Discovery 热门9点档接着播出。